Yeah, so thanks for the invitation. I want to talk about open data travel demand synthesis today and a couple of topics around. So it's going to be quite a bit a mix of different topics, but you will see where we go through the presentation. So I always like to start these presentations in a way like this, that we can look at the situation on the road in 1900, where we see that there was a lot of things going on in the road here in New York. So there's a lot of people interacting. There are some vehicles here, but basically this is a shared space with a lot of interaction. And this, in a way, has changed into a situation like this, where we are moving tons of metal from the suburbs into the city center, and we are moving it back in the afternoon. And all of these vehicles here takes a lot of space. They stand just around 90% of the day. They are not used. And of course, there's a lot of emissions linked to that. And what is interesting to understand here is, and there's, for instance, an interesting book by Peter Norton on fighting traffic, where he describes how it was a fight between different institutions and societal elements that we arrive in such a car-centered situation, is that, well, at any point in time, there could have been a different decision, and we could have said, for instance, we put more focus on collective transport. So this is basically a step-by-step process which is developing. And we have arrived here. Today, we are facing similar challenges because there's a lot of new concepts going on. So we are talking about electrification. We are talking about mobility as a service, mobility on demand. We are talking about automated vehicles. Now we even start talking about urban air mobility, so flying cars, basically. The question here is, what are the benefits and what are the disadvantages of each of these technologies, also of policies, and what is kind of the net benefit of all of this? And this we try to answer through simulations and analysis, and also to guide the policymakers in a way that the positive sides of all of these new policies and technologies will be seen in the future, and we will not have to deal with the negative ones. This is the ideal idea why we are looking at our transport simulations and analysis. Now, how do we do this practically? So traditionally, transport planning was based on classic 4-step models, which means we have certain zones which represent, for instance, municipalities. We have a certain flow, for instance, of commuters between two municipalities, that we look at the peak hours or maybe different time slices of the day and aggregate user groups. So all of this is quite macroscopic, all of this is quite aggregated. And this works if we want to check what benefit do we get if we build a new highway? What are the costs of this? Who will benefit? What is the total benefit of adding this highway? The same goes for a metro line where we move a large flow of people. And this used to be a good tool, but today we are facing a different situation where we have already built a lot of infrastructure, and there's a limit to how much of more highways we can build, how much of lanes we can add, and also of how much of rail lines we can still build. So if we look at what are the trends in mobility, it always has to do with digitalization and making movements of the people more intelligent by providing intelligent, adaptive, dynamic services. So everybody has an app. They can order a car to go from A to B and so on. But this requires that also on our modeling and simulation side, we adapt to this and we are able to represent these phenomena. So what we want is actually to have detailed representation of the daily activity patterns of the people. So what do they do and where and when during one day, and what kind of mode of transports do they use in between? Because this way we can then see for which situations in the daily life does, for instance, an on-demand taxi service make sense or not? Where does a train line make sense? So when we look at agent-based models to solve this problem, we're looking really at the detailed simulation of discrete locations. We look at individual travelers with individual behavior, where we can see any second or any minute during the day what these agents, what these people are doing and how they're interacting the transport system. Now, one big or the first major step, and this is also one of the major topics of this talk for this, is to how to even generate this. So the flows between zones, we can measure this easily somehow from aggregated data. But how do we generate these detailed activity chains for the people? So in France, and I'll show here the example for Lyon, but the same works for Paris or other cities. There we start with the population census, which allows us in quite detailed zones in France to place the people on the map. And also we have social demographic attributes of these people and how they're merged into households. Another step is to use the data set, which is called philosophy, which is basically a database for each municipality of income distributions of the population in deciles. So what we do, because we don't have this information from the census, we attach this income data based on the location. We could also do this based on social demographic attributes, for instance. Now, another thing that is available for us is commuting data. So if we know that the synthetic person lives in a certain municipality, this is basically a large origin destination matrix for all of France, which tells us if you live in a certain municipality, what is the probability that you will work in another municipality? The same goes for your place of education. So we use this data set to sample for each of the persons municipality where they work or where they do their educational activities. Now, the next element that is important are household travel surveys. And here, this is a local one that is performed in Lyon, where we are facing the normal situation of a household travel survey. So somebody would come or call you and tell me, what did you do during one day? And then you would say, well, until 8, I was at home, I was sleeping, then getting ready for work. I took my car, I went to work, stayed there until 5, and then afterwards I went home again. And these activity chains that the people were asked, they can be arbitrarily complex. So this one, for instance, goes to school and then goes to a restaurant here. And these we have as data available together with the social demographic attributes. What we then do is we attach these activity chains to our synthetic persons based on their social demographic attributes. So for instance, a child will receive a different activity chain than their parents. Now, another data set that we have, or two other ones, is Sirene, which is a comprehensive enterprise census of France. So there we have all the companies in the country with their written address, and we have an address database with written addresses and coordinates. If we merge these two, we can find all the locations where these people in the synthetic population will do their activities, like going to a restaurant or to the cinema. And we can enrich these activity chains with this information. So what we arrive at, and I was not going into detail for the methods here, this is written in the corresponding paper, but what we arrive here is a synthetic population, which technically looks like this. We have a list of persons with social demographic attributes and also spatial information. So for Lyon, for instance, here now we see where these people live. So each point is a generated person. Of course, we also have the activity chains, which looks like this, that we have per person. We know exactly what does this person do during one day, activity after activity, when do these activities start and when do they end. And with this, we can already do a lot of analysis. For instance, we can check which persons live within 15 minutes travel time of a hospital. And then we can check what are the social demographic attributes of these persons, for instance. So this is already a rich set for data analysis, but what we are usually interested in is also to simulate this population, to simulate their movements. So what we can add there is, for instance, data from OpenStreetMap to create a road network, as you see here in the background in gray, or use available GTFS data, which is basically the digital version of the public transport schedule. So here, for instance, you see all the commuter rail and metro lines in Lyon. So, and then we put this into a simulation. We will look into this a bit more in detail, but here you basically then see how this population is moving. They are following their activities Every bubble here is one work activity. You see in the background all the cars moving as gray dots, and all the black dots here are the public transport vehicles, for instance. So this is then the ultimate goal of having these synthetic populations. Now, one interesting thing here is, you see I was putting this EDGT, which is the local household travel survey, here to the side, because we can also, instead of it, use the national household travel survey, which is a bit less detailed for the specific regions in France, but which is available as open source. And effectively, all these data sets I was talking about here, they are open source, open data in France. So you can go to the website of the Statistical Office of France, of the Geographic Institute, and you can download all of these data sets on your computer, and you can work with them. Now, what we did here is actually we are starting with open data. The whole code to create this synthetic travel demand from the raw data to the final output is available as open source as well on GitHub. This allows us now to make reproducible research with these agent-based simulations. So this is something that you usually don't have in research with these agent-based simulations today. Usually it is only described really briefly how they were generated. Usually the data is not available. It's not clear which methods have been used. But with this, what we have published, or which is currently under review in this paper, we make it first time possible to really create the synthetic travel demand from raw data to the final output, and everybody can replicate this process in detail. Now, since this is so adaptive, there's a couple of use cases that have emerged. So for instance, at Université Gustave Eiffel in Nantes, they have set up a model of Nantes to do simulations on noise modeling. There is use cases in Lille. They have set up a scenario for Lille, working on road pricing and park and ride applications. There is a use case in Toulouse by Odyssey on the placement of use of shared offices. There is a use case in Rennes by Telae. They are doing simulations on micromobility services. And there's a couple of use cases in Paris. So this is done by Université Gustave Eiffel and École des Ponts, who look at certain scenarios for the development of certain areas in the city and new mobility services. There's IFP Énergie Nouvelle in Paris, which are doing cycling simulations and also have published this here in this paper. And of course, it's us, IRT System X. We are doing simulation also of dynamic mobility services. And for instance, in the thesis of Tarek, we are looking at fleet control through reinforcement learning. And finally, of the use cases that I know of this method that we have published, we are using a synthetic population for Lyon that I was describing already, to look in the project Horizon 2020 project LEAD on low emission first last mile logistics. So you can see there are quite a lot of use cases in France, because this software, this system is completely open, and this has kind of created a nice ecosystem around this software and around this synthetic travel demand in France. But it doesn't end there. So, okay, here's just the repositories on GitHub if you're interested to look into that. But it doesn't end there, because the same methodology we have applied for other cases in the world. So there is one implementation that you can see here on GitHub for Sao Paulo, because surprisingly, there's also all this data that we use in Paris is basically also available in Sao Paulo. Similar case is California. There the data is a bit different, but still we can use almost the same process. So we also have set up this open pipeline from raw data to the final population for California. But there are other use cases. For instance, in Switzerland, there's use cases in Canada, Jakarta, Casablanca. So there's a lot of people who are using this. And I get a lot of requests, probably once every 2 weeks, of somebody else in some other city who wants to set up the system. I give the references how to do it. Usually then the situation is that the data where they want to do it is just not available in this detail. And this is an interesting thing, because for instance, in Germany, this work would not be possible because the data is just not there. In Switzerland, where we have a whole synthetic population for Switzerland, It is possible to do this, but the data provided by the statistical office is unanonymized. So there we were working really with a data set with 8 million residents of Switzerland with their detailed addresses and everything. So this is difficult to publish and work with. So the nice thing in France is that the authorities have acquired the knowledge on anonymization and also anonymizing these data sets and making them available for public use. So this is has really a value for research in this case. Now, coming now to the simulation part, because what we have seen is that there are many actors who are using the synthetic travel demand, but this is intentionally developed independently of the simulator. So for instance, you have seen Tele, they do micro mobility simulations with a different simulator, although most of the use cases make use of MatSim, which I'm describing here. So basically this, and I'm involved in the development of MatSim for more than 4 years, so quite a long time. This is an open source multi-agent transport simulator, and we will see in a minute how this works a bit more in detail. And it is basically available online, so everybody can modify it to their needs, everybody can collaborate to make it better, and there's quite a large community that has evolved around it. So here, this is a bit the academic side. It is mainly developed by ETH Zurich and by TU Berlin, but we are doing quite a lot of work at Systemix on MatSim now as well, but there are a lot of different users, for instance, École des Ponts in Paris, but also worldwide in the University of Pretoria at Stanford. So in total, there's more than 50 research groups which are using MatSim, but it's gaining more and more interest also by companies. So the probably biggest user of MatSim are the Swiss Federal Railways, because they have a macroscopic planning model for their train operations that they perform year by year. But they're getting interested in these small interactions when they have, for instance, a shuttle service that goes to the train station. And then they want to understand these detailed interactions in time and in space between the customers and these dynamic vehicles that drive and have to fulfill a certain service. And this is basically what they're interested in. And this is something that they can only do with MatSim or a similar tool, but not with the classic macroscopic 4-step models. Now, how does MatSim then work when we put our synthetic travel demand in there? So this is where we start. We have these activity chains of all the agents. We then perform a mobility simulation. So all the agents move in the network. They move in the public transport network or on the road network. They perceive certain travel times. They perceive, for instance, one could also use the crowding in the trains. And then they can calculate a value. Is this a beneficial way of performing my daily plan with my travel plans or not? So what they experience, for instance, is congestion. If there are too many vehicles on one link in MatSim, because it is a queue-based simulation, vehicles will get stuck and we will have congestion propagating through the network. And this is what the agents will perceive. There will be delays, and they try to avoid these delays. And they can do this by performing decision making. So once they have experienced how their current configuration of the daily plan works, they can make decisions. For instance, to say, now I want to leave a couple of minutes earlier or later to catch my train. Or maybe this was too long a way of walking, so here I now take a bus. So they can change departure times, they can change transport modes and other things in their daily plans to maybe try to find a better option for how to connect their activities during the day. Now we do this in a loop. So we simulate then, we update the synthetic population with the new departure times and modes. We do this mobility simulation again, different travel times emerge, agents make decisions based on these travel times, and we update the demand again, and so on. So we perform this loop for a long time. And then we see, for instance, here some simulation where we were looking at the taxi service in a city. And this taxi service is newly introduced. So if we look at the requests, at the beginning we have no requests. Then agents are more and more choosing this service step by step, and at the end we stabilize at a certain value. So this is then the basic idea. If we run this cycle a lot of times, all the travel characteristics will stabilize, the distribution of travel times, the mode shares in the system, and so on. And then at some point, when we have a sufficient number of iterations, we do the analysis. And what you see here, for instance, is an analysis for calibration, where we would have the distance covered by each of the trips in the simulation. And then we see the mode share. So at the Euclidean distance of 5 kilometers here, for instance, we had a mode share of 40%. And then we can compare the simulation output, which is the dark line, with the dotted line, which is the reference data. But also then we do the analysis for the baseline simulation. Then we, for instance, add a new metro line, add a new taxi service, and we analyze how do people change, what kind of changes did they make in their travel plans, which lines are used more or less now. And like this, we can construct scenarios and analyze what impact do the specific elements in this scenario have on the transport system. Now, a couple of examples. So for instance, this is something I did when I was still at ETH, but visiting the lab of Nicolas Colombel in Paris. There we were just using the synthetic population generated for the Ile de France region around Paris. And what you see is the morning when agents now in a couple of seconds when they wake up, and now they start moving, you see all the cars moving, and on the links you see how many CO2 emissions were produced. The interesting thing here is that we can know exactly, if we look at a certain area, for instance here, which agents are producing these CO2 emissions. Like for instance, where do they live? What social demographic attributes do they have? Likewise, we can check which agents are there at a certain time, especially if we don't look at CO2, but at noise emissions, for instance, or at particular matter. We can estimate which agents are there when these emissions are created. So who is affected by these emissions? Also, what is the social demographic groups? What is, where do they live? Where do they work? And so on. So we can make this detailed agent-to-agent interaction. We can find who is imposing emissions on which other agent, for instance. And this is quite a rich tool that allows us to perform a lot of analysis and of course then also look at policies later on. This is another use case where we were looking at Paris, and we said that all the people who are using cars or public transport before, they may now choose to use an automated taxi service in Paris. This links directly to the presentation that I gave in the beginning of this seminar series, where I was showing presentations where we did similar simulations in Zurich and came to the conclusion, basically, an automated taxi system in Zurich would be not actually beneficial for the whole transport system in terms of emissions and distance driven. And here we did a similar analysis for Paris. So people make a decision to either use their mode of transport that they were using before or use the automated taxi now. This is then nice to visualize because here we see all the vehicles, how they are driving in the network. We see these bubbles where people get picked up and dropped off. But effectively, we are more interested in more aggregate measures. So what we see here then is, if we look at the orange graph, that we can modify the fleet size. We see for very low fleet sizes, waiting times will be really high because there's not many vehicles. So only few people will use these vehicles. So these are actually in thousands, 14,000 will use, 14,000 rides we will have for this service. If the fleet size gets really large, the costs for the operator are high, which means that he needs to ask higher prices. And this is also why people like it then a bit less to use the service compared to this kind of maximum demand point here at the fleet size of 5,000 vehicles, which would then be interesting for the people. Yeah, so they would be there. We would see kind of a demand of about 17,500 rides with 5,000 vehicles driving around in Paris. Probably we will not be in a situation where we have 5,000 automated taxis driving in Paris, but at least this is giving us a kind of a order of magnitude in which we have to think. And especially this also tells us this is only half of the rides that would be theoretically possible So we see in this study already, just by giving agents the choice and having our best knowledge on the preference of the people, that only half of the people who could actually use an automated taxi for their trips would be willing to use it, just because of the structure of their daily plans and their preferences. Another case, which is bringing us a bit to the closer future. So the Grand Paris Express is one of the largest infrastructure projects in Europe. And we can also put this into the simulation, for instance, and then we can do an analysis. If we have these new metro lines, how will the passenger number for the other metro lines, for the other train lines change, for instance? So the idea here is really to build this metro ring around Paris and then connect also the city with the surrounding region by these kind of lateral connections here. This is also possible because the Société Grand Paris, which is in charge of planning this system, is also putting available as open data all the stop locations, the planned frequencies for all the lines, and additional information. So basically, we can take all of this data, also put it as open data in this pipeline that we already have in open data, and then create this open data simulation of the Grand Paris Express with our synthetic population. This is kind of a side project that was started at some point. Let's see if we manage to still make an interesting paper out of this. This could, for instance, be linked to actually the question, how do people reach these new stations? How would the bus lines need to be designed? Should there be shuttle services and so on? So there's a couple of interesting questions to be asked around that. Now, at the end, I want to, or for the last part, I want to talk a bit more in detail about the currently ongoing study in a Horizon 2020 project, which is LEAD, which I already mentioned. It's all about low emission adaptive logistics solutions. So there's a couple of cities all around Europe involved, and each city has kind of a modeling simulation component and then a real world living lab implementation component. We are in charge of Lyon in this project, and I want to talk a bit about the simulation part and some first steps that we have done in this direction. So what we are looking at here is Confluence, which is a borough in Lyon, which is kind of connecting here the old city on this peninsula. So in the north of this area, this is already quite a residential area. In the south of this area, this is more like shopping centers, industry, and so business land use. But it will be restructured in the coming years to also be more focused on residential use. And what we're interested in here is to know a bit, how can we put in place sustainable logistics solutions today, but solutions that also stay sustainable for the future. So one idea here is to put an urban consolidation center and look at parcel deliveries. This is kind of the first step in the study that we are looking at. So the idea is that today there's a couple of operators which are bringing parcels to the population in this area, but they do this individually, and they do this, well, sometimes with electric vehicles, sometimes with non-electric vehicles. But the idea then would be to have an urban consolidation center where these operators bring the parcels, and from this urban consolidation center, we use, for instance, small delivery robots or cargo bikes to deliver these parcels emission-free in this area. Now, how can we make use of the synthetic travel demand that I was introducing before in this context here? And this will get a bit more technical now. So what we have is a synthetic population. What we also have is a survey. Unfortunately, well, the fortunate part is that we have a survey on how people make purchases for the population of Lyon. So this is really specific for the area. The unfortunate part is that we don't have the raw data, but we can access the report and get some marginal data. And this is also a nice way to do it, because like this, we can stay on the side of open data in a way, because this report is published. So what we have in this report is then, for instance, the number of purchases per year per household for certain social professional groups. So you see, for instance, here some kind of commercial people, they have more than 20 purchases per year, while people without an activity or retired people, they only have 10 purchases per year. So here we're talking about purchases which are not done by the persons themselves in a shop, but we are basically talking about purchases where people would need to pick up something in a shop, or where people just letting things being delivered to their place of residence. So here we kind of have these marginal numbers per social professional category. We have similar marginal matrices for the combination of age and for the social professional group. So for instance, you see, but we don't have retired people between 18 and 34 years, so there's no purchases in this group. But for instance, the highest group is here, for instance, the commerciants between the age of 18 and 34, which have 45 purchases per year on average. And like this, we can look at every combination here. We have a similar matrix for the household size, which is crossed with the social professional group. So for instance, here, these are workers with a household of more than 4 people. They have, for instance, 29 purchases per year. So this gives us kind of marginal numbers for certain categories, for certain strata of the population. Another information that we get from the survey is the home delivery probability. So let's say that one household has a certain purchase or has a certain number of purchases per year. How many of them are actually delivered at home, or how many are picked up in a shop, for instance? So you can see that, for instance, here the retired people, they have quite a lot of deliveries to home, while workers, they don't deliver it to home, but maybe they pick up their purchases, for instance, in a shop. So this is kind of the technical component. Since we have our synthetic population, we can now look at these strata. So when we look at NAHS, you see, for instance, this is the number of people which have a certain social professional category, which have a certain age class, which have a certain household size class, and which have a certain social professional category. If you want to find, what we want to find is the number of parcels that these households generate on average. So we multiply the number of these households in this stratum with the number of people in this stratum with the number of parcels that they generate, and we should arrive at this marginal number of parcels. So here we sum over the age class, which means we compare the number of parcels in total with the marginal for household size and social professional class. So this is basically this table here, household size, social professional class. Here we have these marginal numbers. This would be the C. If we sum all over them, we should arrive at this number. We can define a similar constraint for all of these tables that we have seen. And we also know if we sum over all the people multiplied by their average number of parcels, we will arrive at the total number of parcels per year, which is on average 14 for the whole population. This we also know from the survey. Now, iterative proportional fitting is then a method to find these weights here. So we basically say, we count this number of people, we have this marginal number, and then we find which weight should we put here so we can actually match this constraint. For a certain combination of household size and social professional class, then we go to the next combination, we go to the next constraint, and so on. And if we do this for a long time, this is iterative proportional fitting, we arrive at these weights, and then we know for each of these strata how many purchases do they do per year. If we use this value, divide by 365, multiply by this probability of home delivery, we actually get this number, this mean number per year for each of these stratum of each household, how many parcels they will receive. Now, this is the mean number per year. This doesn't tell us yet for a particular day how many parcels will a certain household have. And we don't have information on this. So this would be a distribution like the majority of people receives no parcel. Some people receive one parcel, a few, maybe two, and even less people receive 3 parcels on a particular day. But we don't have this information. What we know is we know the mean. How many parcels should they receive in the mean? We know that this distribution is discrete, 0, 1, 2, 3 parcels. And we know that it must be a positive number. What we can do is we can impose the maximum entropy distribution for this situation and then generate the number of parcels based on this. So in most cases, we have 0 parcels, in some we have 1, and so on. Now, long story, how this works technically. If we just look at the result, we can now see here that all the parcels generated according to this process for the region around Lyon. We can zoom in even further. This is the city of Lyon. We see all the parcels that we have generated. And then we look at the confluence area. And there you see what I was explaining before. So here we have kind of the residential part. And there we also see that we create quite some parcels. Well, this is the business part for the time being, where we don't really generate any parcels with this approach because nobody's living there. So now, since we have this, now we have an idea of how many parcels are even generated, because this we didn't even know before. And like accordingly, we also don't know which kind of travel distances and externalities are connected to these parcel deliveries. But so here we are already one step further. An interesting observation here is now that we also can check for each of the households who has a parcel delivery on a particular day, when is there at least one person at home in these households that is over 14 years old? So when is there a person that could actually receive this parcel? So what we did here is to impose this distribution, basically when households can receive a package. We said, okay, before 5:30 here, nobody wants to receive a package. And also here between 9:30 or 9:45 something, nobody wants to receive a parcel. So we were setting these values to 0. But for all other times of the day, we see that, okay, in the early morning, in the late evening, there's almost 100% of households where at least one person would be there to receive a package. And this value, this drops to almost 40% here, for instance, at 15 o'clock in the afternoon. But what we can do here is to envision a system, and this is our first experiment, where we have this consolidation center. We have delivery robots which deliver the parcels in an optimal way, such that they have to bring the package when somebody is at home in these households which have ordered a certain parcel. Now, what we need to do here is to solve a routing problem with time windows. So basically the question is, we have a certain vehicle and we have a number of households that we need to visit. How to do this in an optimal way? This is basically solving the vehicle routing problem. And we define the time windows, because also these vehicles, they should arrive at a certain time when somebody is at home. These can be multiple time windows per day. And of course, we don't only look at one vehicle, but we look at multiple vehicles and a larger number of households, a larger number of parcels that need to be delivered. Now, if we look at the first simple case study here, we can first look at, for confluence, how many parcels do we have? And we have generated 101 parcels that we have on average per day. We can say that each parcel has a size of 1. We have 10 delivery robots. Each vehicle can take 5 of these parcels with size 1, and they drive with about 10 kilometers per hour. We then also say it takes time to pick up a parcel at the depot, so the consolidation center, and the interaction with the customer. With each customer takes about 5 minutes because the customer needs to come down from their flat and so on. And the idea here is to minimize the driven distance, because then kind of from the operator side, this would be an efficient system. Now, if we do this, if we then solve the vehicle routing problem with time windows, we find that to deliver all of these 101 parcels in Confluence, we need three vehicles, which would cover a total distance of 41.35 kilometers on a particular day. And we can also visualize this. So here you see in the three colors, you see the three different vehicles. They go here to the distribution center, where you see when these black bubbles pop up, they're picking up parcels, and then they go to the customer and deliver the parcel here on the specific link where the customer is living. And of course, this gives us now a large range of potential future studies. So first, we want to see what happens if we kind of model the development of this area here, where we will have more residential use. We can check different vehicle types. We can check different speeds. We can assume that these are cargo bikes, where will have different requirements on the time windows and so on. So there's quite a large variety of things we can do here in this first part of the study. But there's also a second part of this lead study that I want to mention. So we also make a connection with MassGT, which is a simulator developed by TU Delft, which is actually simulating the decision-making of companies with respect to certain transport policies. There, the idea is to make the connection between these two simulators, where we could say, okay, not only do we have this urban consolidation center, this is available for the companies, for the delivery companies, but we also put this low emission zone. So we say this will cost them if they enter this zone with their trucks. And what MassGT then does is to simulate the behavior of these companies and of these decision makers there. So maybe they would decide then to avoid this emission zone and actually go to the urban consolidation center, make use of the service of the urban consolidation center. And then we could see what is kind of the effect of these policies. And this is something that we are starting to work on now, to establish this connection between MathSim and MassGT, where MassGT reacts to certain policy settings, simulates the behavior, and then we can feed back the effects from MathSim to this modeling system, which will mean travel times will change. Maybe the policies could be based on certain, could be adaptively based on certain emission KPIs and so on. So this is kind of the longer term perspective now in the project lead. So just to finish, there's also other projects going on at ERT System X around MathSim and synthetic populations. So for instance, we are looking at on-demand mobility services in a couple of projects, trying to find efficient algorithms, testing algorithms, how these services can be operated. And one other topic for which we don't really have the time here would be also automatic calibration. Maybe there will be also some questions about this, because there we also need to answer the question, how do we actually adapt these behavioral models of all the people, of all the synthetic people in the simulation, such that we represent well the behavior in reality. Okay, so this was a bit an overview about the synthetic travel demand and then our applications around that. I hope this was interesting, and well, now it's time for your questions if you have any. Thank you.